Hi everyone, thanks for tuning in to this CNCF maintainer track session on OpenEBS. OpenEBS joined CNCF about a year ago and just completed its annual review, and it's on its way to uh, clear the incubation stage. I'm actually delighted to present this talk along with Vishnu here today. Both of us are available on Slack, Kubernetes Slack. Our IDs are there. You can reach out to us for any questions related to the session, as well as if you have any questions related to running stateful applications in Kubernetes. We are really excited about the possibilities that Kubernetes offers for running stateful workloads. Just a little bit of MayaData, where which actually sponsors both of us. We both completely work in open source and with the community. Um, MayaData is also like one of the top contributors in the CNCF. It has donated OpenEBS that we will talk a little bit more today, and it recently also founded and along with other companies donated Litmus as another project. Litmus is used for enabling chaos engineering in a Kubernetes native way in Kubernetes clusters. It's actually both for stateful and stateless workloads. Apart from working on OpenEBS and Litmus projects, Vishnu and I also work on several other Kubernetes ecosystem projects. For example, I'm recently contributing to the NFS Provisioners project in the Kubernetes 6, whereas Vishnu is actively involved in Valero, which is a disaster recovery or like a migration tool for Kubernetes applications, both stateless as well as stateful. Just to quickly give you a snapshot of what we are going to cover today, we'll recap the state of stateful workloads in Kubernetes and some of the challenges or some of the motivations that actually drove us to write a new type of storage that we call as container attached storage, or you can kind of call it as hyperconverged storage. In fact, hyperconverged storage is the category that CNCF white paper uses to include OpenEBS as one of the storage options that are available. We talk about like several engines that OpenEBS supports, and this kind of stems from the concept of container attached storage, and we'll probably see why we need multiple storage engines as well as we go through the talk. And we also present a few end user stories that have adopted the container attached storage concept and actually are running stateful workloads in Kubernetes as we speak. With that, I have a lot to cover, so I will jump right in to this one. If some of you are just getting started with the stateful workloads, it's pretty straightforward as of today that you start with PV, PVC, storage class, and CSI. These are the main constructs that you need to know that provide you these volumes for your stateful workloads. But for some of us who have been around in the Kubernetes community, we have seen the evolution from volumes to entry volumes to flex volumes, then dynamic provisioning by the external provisioner. It's been a journey, and in fact, I talk about this a little more in the rest of the presentation, but Conway's law is something that keeps popping up every now and then. In fact, the move of the project to shift all the entry volumes to their own CSI drivers and the evolution of the CSI drivers itself is a manifestation of how decoupled storage drivers are splitting the storage volume code from the Kubernetes monorepo to its own repos is increasing the agility of making the Kubernetes releases and as well as adding more drivers as we move along. CSI has become a de facto standard now. A lot of people use it. Both vendors and users are getting comfortable with it. But it doesn't end there. It's just in its early stages of defining the spec. There are a lot of enhancements that are being worked on right now. For example, if you want to use capacity-based scheduling, or the concept of pools, which is something very common for the storage vendors, but not so much in the Kubernetes community yet. All those things are definitely coming in. So if you are interested in contributing to any of these in terms of use cases or code or like the spec, please join one of the working group calls or like the mailing aliases or the Slack channels. One of my favorite is the data protection that recently started, and it definitely needs a lot more help. With that, I think this kind of presents one of the architecture that's kind of becoming as a good stepping stone to introduce stateful workloads in Kubernetes. You basically use CSI to connect any of your like externally attached storage. But there are a few challenges with this architecture. We'll try to go into details of each of them, but it suffices to say that the Kubernetes enables a loosely coupled microservices architecture, but when we look at the storage that is serving these applications, that itself is actually developed using monolithic architecture and for a different time and period. The loosely coupled and the agility that you get, the auto scaling capabilities like both scaling up and scaling down that you get by running in a microservices way, you kind of lose it when you go down and try to put everything into this shared storage, and basically you lose your agility as well, right? One of the things that happens is the shared storage will have to mix and match the different parameters while serving the different workloads. There could be like different demands for, could be like critical workloads versus less critical workloads. All of them get the same kind of storage. You need to handhold and make that happen. So this is actually a slightly older survey, and I think a new survey is probably going to hit around the corner, maybe like in this event that we are speaking as well. But one of the interesting things that I noticed here is, even though Kubernetes was developed for stateless workloads, state is quickly becoming very popular or being used in many of the Kubernetes clusters. This shows a wide range of different storage products that are used. You can kind of divide this into a couple of categories. For example, to run your Kubernetes workers, you do need storage. So some of these cloud provider volumes could be that kind of a storage, but there are other projects here like OpenEBS or Rook cluster, Portworx. These are the projects that are custom made to provide storage to your stateful workloads. So if users are using those products here, or if they're responding that they're either evaluating or put into production, that means they're definitely running stateful workloads in Kubernetes. Another interesting thing to note is a lot of folks are evaluating the container storage, container attached storage option, and OpenEBS is one of the leading implementation of that particular category of storage. We'll see what that is in a little bit. So I briefly mentioned about Conway's law that, while talking about the storage or the evolution of the CSI drivers itself. So just to recap that a bit, it's basically a cultural shift that we are seeing overall in the industry from every layer. At the if we have to briefly explain what this is, it's about the way we compose our teams is the way we develop our applications. The shift from having specialized teams to making the functional teams, where you kind of put experts from different categories so that you can actually develop independent services is the norm right now. This, you can kind of call this as a DevOps culture, or it's the Conway's layer at play. The diagrams that I'm showing here are from a very good thought piece from ThoughtWorks. So do please check it out. And this is not just a theory. You can see that within CNCF, there are a lot of end-user stories where this has become a practice. For example, this is again from the previous KubeCon, where Stephen Prover at Bloomberg is describing how they, as a platform engineer, he's supporting several thousands of small teams. Sometimes the team could be just comprised of two who own up a service. And to kind of enable such large teams with a small platform team, you need to have very loosely coupled architecture, just like in your team, even with the infrastructure products that you give. Open source and the loosely coupled architectures are the way to kind of make this happen. And a lot of the companies that kind of have adopted Kubernetes actually see that power of ability or the ability to kind of enable such kind of two pizza teams is what they call. I would strongly recommend to watch the video. I kind of highlighted the places where Stephen Bower talks about the data management and how they have moved away from shared to distributor, shared to per workload stacks. So this is the kind of way in which Conway's law applies to data management itself. Couple of things to note here is, instead of using a monolithic database, as we go towards more specialized teams, each team wants to have its own type of database instead of basically like the database that really suits their workload or engine. Instead of trying to force fit their application to use an infrastructure that's already available and it may not really deliver on its promises. This is becoming quite common. In fact, like talk to a lot of community members where OLAP databases themselves are getting split. I think one of the main challenges that they're trying to solve is the scaling problem. And within Kubernetes, you have this promise of auto scaling, which is not just about scaling up, but also scaling down. And that can only happen when you kind of break down a monolithic databases into smaller databases. So one of the use cases that we are currently working on is splitting a monolithic database that stores hundreds and thousands of user data into a single database with 100 TB volume into like basically a microservices based OLAP with 100 different pods trying to write to a 1 TB volume and have a sharding of like the user data into different things. So you can kind of move the user data into some of these pods, and you can kind of release the data or like some of the volumes if you are scaling down as well, which is kind of a humongous task if you are trying to do with the traditional way of like having a monolithic database on top of which or you're basically running that on a shared storage platform. So a few of the things that happen with the shared storage platform are also what we call as data gravity. Data gravity is this notion where the storage system that you use has a tendency to pull in all the applications towards it. This happens initially probably based on the familiarity with that system, but then as you put in more data and for latency reasons, you have to be closer to that storage system, and it kind of locks you into a technology that will be hard to kind of move away from, and it takes a lot of operational cost as well to think of something else. You kind of get locked in because of the data gravity, and you end up spending more as well. While Conway's law and like data gravity or some things that you can easily relate to by your day-to-day operations, there are a few other things that are happening as well in terms of software and hardware. So for example, like the evolution of the hardware systems that are coming out, it's pretty common now to kind of get an hardware with the 96 core CPU with 1 TB flash drive, like the one that I showed here from Supermicro. But the thing about such kind of high powered hardware is that you cannot use an application that was written to run on 8 to 16 core and try to put it on a 96 core machine and expect it to deliver at a higher performance. You do need to change the way you write the application, or like the way you architect that one, and I'll show you some examples. So for example, the SCSI architecture has been around for a while, and if you are trying to use that to access the data, then you're kind of limited by a maximum of 1K commands that you can process in parallel, versus using an NVMe that allows you to process around 64K commands in parallel. And also, like using this NVMe, which is like a more recent technology, or like the protocol that's kind of becoming very popular, especially with NVMe over Fabric becoming available via different cloud providers, as well as you can kind of just buy those kind of hardware as well now. It allows you to implement that in a user space, as well as it's kind of easy to implement compared to like implementing a SaaS driver. You can completely bypass the kernel. There are some use cases where you may want to do that. For example, like this chart from Brendan Gerg kind of shows that as you increase as you increase the number of system calls, you end up increasing the latency of, or like it starts degrading the performance. So one way to counter that would be go towards using user space technologies, and actually like the languages now support that. For example, like Rust is one thing that we use for developing the MayaStore. It's actually a storage engine that we have written completely in user space that makes use of NVMe as well as writing in the user space, but gets the same performance that you would get by developing it in the kernel, right? So talking about the kernel, it's not just about the physical interfaces, but it's also about the algorithms that are changing. For example, pole mode driver is something that's kind of becoming popular to scale up the applications. FIO, or sorry, AIO, that was kind of pretty common, kind of peaks when you go around 8 cores. So IOU ring and IOU ring pole are things that you want to use in your application to get most of it. This is not just about storage. We see that this kind of analysis and reworks are happening in other stacks as well. For example, ScyllaDB and VPP from the network domain are all having some kind of rewrites to make use of the latest technology and provide higher transactions per second. And we think that the same thing applies to storage as well. And that's what actually motivated us to come up with the container attached storage. So, few things that we kind of considered. We are anyway trying to rewrite the applications. Why not also think about how do we do the control plane? And when we started OpenEBS a few years ago, Kubernetes was just on the rise, but we saw the potential of the way in which you can write the control plane in a declarative way. So we have decoupled the control plane of the storage engines to be handled by Kubernetes itself. So in some sense, Kubernetes is actually your orchestrator for the storage as well, especially if you're using OpenEBS. And it comes with the benefits of being a completely declarative way of operating it. And then you can kind of put GitOps, which is kind of the way you manage your infrastructure these days, right? The microservices pattern is another thing that we see provides you the needed agility. So the storage that we kind of saw that shared storage is kind of now split into microservices-based storage architecture. Kubernetes and microservices architecture are some things that we adopted, as well as trying to make use of the latest hardware that's available so that we get better performance for the storage that we invest in, right? When we developed OpenEBS, one of the interesting thing that came out of the whole thing was it's the ease of operations. So the persona of folks that are running the storage now is also changing. There are no longer specialized storage administrators who are going to run stateful workloads. It's going to be the Kubernetes SRE, and Kubernetes SREs will be more comfortable if you have a storage that speaks the Kubernetes native language. So just like how they get comfortable with the networking concepts and the scheduling concepts by modifying some YAML files, you can actually do that for the storage by using this new category of storage that we call as cache. So to just give a snapshot of that one, instead of trying to put the storage or like the state outside of the Kubernetes cluster, you have a lot of power available with your Kubernetes worker nodes. So you can make use of the storage available with them to drive your stateful workloads. And this all happens in a microservices way, where each application gets its own storage controller instead of having like some shared system. So even in case you want to move one workload from one cluster to another cluster, it's going to be easy. So the state moves along with the application to another cluster. And we kind of realized as we started developing that one storage engine does not meet the needs of all the applications that users are bringing to the Kubernetes clusters. In fact, the applications themselves are changing. They're becoming more distributed in nature. So we came up with a different set of applications that we want, right? These are a huge list of adopters that have already started using OpenEBS. Just want to highlight a couple of them. The first one is the Optoro, which actually uses this hyperconverged mode of storage. And the main reason for them to move is not having a complicated distributed system outside of the Kubernetes cluster to manage for their stateful workloads. And as you can see, they've migrated most of their stateful stack into Kubernetes itself. This is an end user company. Similarly, we
Thanks, Kiran, for giving us the background, how the story is evolving, and the workloads are changing, and how the CPU calls, the system calls are all like having a cost on the CPU cycles. So this is one of the slide where we want to mention about how the applications are themselves kind of doing the replication, and then once it has the storage with it. So to provide the storage to these applications, which are from the storage, which is hyperconverged, attached to the nodes itself. Like OpenEBS have a couple of flavors: Hostpath, block device, and local ZFS. In the next slide, I will explain about how the workloads are kind of having STS is one of the workload, and it have multiple replicas of the microservice which it is want to run, and the pods now have their own PVCs, and now the storage provisioner is the one who will be like giving out the data, the storage carved out from the devices, the storage device attached to the node. So that's what we have. The PV will be created by the storage provisioners. So the three couple of flavors are having is the local PV is the one where the OpenEBS, this provisioner uses the entire disk will be given as a raw device to the pod, or as mounted into a file path, into the mount path as a file system. The other part we have the ZFS local P, which is we have a CSS driver which allows to once the pools are created, the ZFS pools are created on the nodes. So this CSS provisioner will carve out a JEDWAL of the volume or the ZFS data set and mount it into the pod. So the other one is the local PV. In this, the host path is the where the provisioner creates dynamically on the demand the directories and attach it to the pod. And also on the during deprovision time, it takes care of deleting them and takes care of deleting the data as well. So this slide is about where the apps which want the storage features from the engines itself. So where the app is kind of having using the storage from using a PVC and then have a PV target. So from the previous slides, we saw how the loosely coupled is really helps in bringing these microservices and then easy to manage, right? So the OpenEBS have again the cache architecture have three flavors of that, like Ziva, CStore, and MayaStore, where there will be like target pods and then the replica pods, which are providing the storage to these applications, and they are again maintained in declarative way using the Kubernetes YAMLs itself. So Kubernetes is a kind of orchestrator. Once this OpenEBS provision creates the YAMLs and then set some the node definitions and the details in the YAMLs. So Kubernetes orchestrator itself will make sure that will have the target pod and the replica pods running in the nodes. So in this slide, we have a deployment, and there are multiple copies of it, and we have a pod, and then the PVC is the storage requirements, and then the PV is now the OpenEBS provisioner comes into picture here, where there is a iSCSI target it creates, which in this case, even if the pods moved from different nodes across the nodes due to the iSCSI target can connect over the network. So this target running in different node also, it helps to get the storage mounted, and when the storage is available on three nodes, when due to as we see here, the three copies of the data is kept in three different nodes. So even a node goes down where one copy is there, once it comes back, the target takes care of rebuilding the data into the one which went down and came up. So one of the engine is so here we are explaining the CStore. Here, if you see towards the right side, there are like set of disks which are the admin use them and create a CStore pool, and then creates the storage classes. So now when the PV is the PVC request comes to the CSA driver, the request comes, the CSA driver comes into picture and creates a iSCSI target, and then this will be attached to the node where the application pod is running through iSCSI protocol, and then it gets mounted into the pod. So the MayaStore is our next gen OpenEBS storage engine, which provides a low latency and provides a high, which is a pool mode driver, and it's flexible to work with any kind of disk, even with NVMe or SCSI disk. And if you see the middle one, there are like FIO providing awesome numbers with 80K for each FIO thread here. Given that the data production, the data in terms of disaster recovery is how we protect the data, how we recover the data. So OpenEBS storage engines have their own plugins based out of Valero. We have OpenEBS has the Valero plugins, which allows to take the backup of the protect the application YAMLs along with the data. And also this works, the OpenEBS volumes can be actually, along the applications can be protected using the Kasten or the Kubera, the other data migration services which are available. Yeah. So with that, we have open for question and answers, and here are the links which you get more material, and the engineering team and then our users are active on the Slack channels in the Kubernetes, and feel free to drop in any questions. And with this, thanks a lot for joining this session.
Hi everyone. We do have a lot of questions that have come in already, so we'll try to take them up. Thanks for joining today and posting the questions. One question has repeated multiple times. It's about the slides. Yes, they are going to be uploaded on the schedule in a moment, and we'll also share them on the Slack channel for maintainer track sessions. The second question was related to, are people using OpenEBS in production? Is it good to put critical workloads? The answer is yes. I think the last slide talks about the different users that have already put it into production. Also, there's an end user community that's come up. It's called Data on Kubernetes. Please feel free to join there and learn from other end users. It's not just about OpenEBS, but it's generally about running data on Kubernetes itself. So there's a lot of material there that can help you. I think the link will be posted shortly on the chat windows here. So one of the interesting questions, Vita, probably you can take this, is about what are the features that have released as part of OpenEBS 2.0. Can you start by talking about your favorite features? Uh, Vishnu, you may be on mute, I guess. So can you check that? So while he settles that one, I can probably talk about a couple of things that I really is about the new flavor of local PV that we have just released, which can help you enforce capacity restrictions on the host path volumes. And also we are working towards a CSI driver for host path volumes. So that's a great thing to check out. It also has fixes for the Jiva volume, stability fixes in terms of reclaiming the space that usually Jiva takes in for creating internal snapshots. In addition, CStore has enhanced greatly in terms of day two operations. And now you can control the disks to be replaced, as well as the expanding the pool with additional disks. All those features have come in as well. Cool. Let me take another question now. So this is about a deployment pattern. The question is, if there are a large number of nodes to have both storage and KATS in the same cluster nodes, it is a good use case to horizontally want to take this up. In case I'm not able to hear him. So I think it's through Valero integration. There are some, you can also use CSI to kind of take the snapshots and clone them for taking the backups within the cluster. But if you want to move them out of the cluster, we use Valero, which is great for helping you take a snapshot of the data along with the applications and then send it out of the cluster, and ability to restore and all those features are available. You can even schedule the backups. I think I got most of the questions. Yeah, so there is one question about when should we use local storage or shared storage provided by OpenEBS? Local storage is good for applications that can do the that can handle high availability or failure of a node. This is a good example, like say MongoDB is a great example, or Cassandra is another good example. Cassandra or MongoDB are capable of handling the node failures, so local PV is a great choice. For these distributed applications, what you really need is low latency storage volumes. A related question on this is, uh, if a node goes down and if a pod gets stuck, what do we do? So there are a couple of things. If you use just like a regular stateful set, then it's possible that you kind of are stuck with that node. So there are some manual operations required to kind of identify that the pod is not getting scheduled because a node is not there. Delete the pod and let it schedule. But at the same time, all these things can also be automated by operators. For example, if you're using Cassandra operator instead of using a Cassandra stateful set, that can take care of this for you easily. One other thing that's happening within the Kubernetes community is to enhance the support for stateful sets, where better PVC management is coming up. So it's definitely worth checking out, and we are going to help you with writing those operators if you need them. Another question related to local PVs is, between host part device or ZFS, which one to pick up? I do have like one slide that I didn't present here that kind of talks about the differences, but to quickly provide the answer to that one, host path is when you have a lot of space on your node coming from a single device, or like from the operating system disk itself, but you don't have a choice in your cloud provider or your environment. Maybe like you're creating from OpenStack where you cannot attach external devices. Host path is a great choice. Device and ZFS is when, if you have devices, like for example, like some boxes come with 8 drives or like 9 drives, that you can dedicate, or by the partitioning them or directly to a workload. That's a good time to use device. ZFS is when you have, let's say like hard disks or that are available on a node, and you want to have resiliency or protect against the um, issues that are coming up with the disk. So this, you can mirror the two disks and create volumes on top of it. I think that's all the questions we had today on this chat to take.
Thank you. If you are the leader, press star now.
I'm speaking, but I can't hear you, Kiran.
Thanks. Yeah.
Okay, so can you repeat the question? Now I can hear you.
Yeah, the question was on data protection. What are the enhancements that are happening in the data protection aspect?
Yep, right. Yeah, we used the Valero as the tool, open source tool, which will be used for backing up the applications along with the data. So with OpenEBS, we have the CStore plugin for Valero, which allows us to take incremental snapshots of the CStore volumes, and then it allows to, it sends the data, and then during restore time, the entire application will be restored, and then it has to be as well. So, and it is very well tested in our PCE environment. So it's safe to use with the production environment.
Thanks, Vita. The other question is on, again, this is related to data protection. Is OpenEBS used in production, and where you have to avoid the data loss in all situations?
Right. So from the adapters list, we have a lot of users using it in production, and the data protection which the strategies they apply is they take the local snapshots, and then they also send it to the S3 location, any S3 compatible location, and they'll restore from there. So we had even few cases where from snapshot data has been recovered. Yes,
All right.
okay.
There's a question here about like 2.0 features, and will we get into the internal support that? Yes, there is a blog that's going to be soon published on that aspect. I'll reach out to you, Oliver. Thanks for asking this question, and thanks for supporting OpenEBS as an end user and also contributing to the Helm charts. Thank you.
Regarding 2.2 features, did we covered about the Jiva? So the Jiva has a new.
So this a question about comparison between OpenEBS, Longhorn, and Rook. In fact, as part of the annual review, we have compared all these three options. I can share that. Richard, if you could reach out to me on the Slack, I can give you to the link to that one. That will be. Thanks for asking that question. There's a question about MayaStore. Yes, so MayaStore is really geared towards NVMe based architecture, especially when you have nodes with high CPU, high number of cores, and disks that can provide you a lot of IOPS. MayaStore is definitely the answer. Louis is asking, can I use OpenEBS outside of the Kubernetes? At this moment, we do not have inbuilt support, but there have been some community members who have modified the way the volume services are exposed so that they can use it outside of the Kubernetes cluster. It's definitely possible. It's not inbuilt into the project itself. There is a question about what was the performance like for Postgres using OpenEBS from Chris. Chris, there's a fantastic blog by Postgres end user who have been actually running Postgres, and I'll probably share that link with you. It was also in the slides. Again, you can use Postgres with the different types of storage engines. So if you're using with obviously local PV, there's no degradation. And also with CStore, there's some amount of degradation because of the network latencies in replicating the data. So I do have in a CNCF webinar where I have shared some of these pbench metrics. I can probably share that with you. So the question is from Praveen here. Are replicas used only for data availability, or can they also be used for load balancing? In the cache architecture, they're primarily used for data availability at the moment, but we are thinking of some or solutions where they can be used for load balancing, especially for providing read-write many kind of use cases. So there's this great question from Oliver. Does it make sense to combine OpenEBS and Rook at all? Yes. So OpenEBS is a collection of data engines. We are definitely looking forward to see how to integrate these data engines as operators in Rook. It's definitely happening. Does OpenEBS work with the OpenShift 3.11? Where there is Kubernetes 1.11. There is a, yeah, we prefer using the latest version of Kubernetes, but we have OpenEBS versions that we still support that works with the 3.11 and with Kubernetes 1.11 as well. There's another question related to, let me see. MayaStore and compare it with CStore. In terms of architecture, the deployment, it is similar. MayaStore also has something called as Nexus, which acts like a target and takes care of replicating it to different volumes. But the differences come in terms of the performance. We basically use TPDK as well as ability to use lockless ring mechanisms to provide high performance there for the IOs. It also supports iSCSI as well as NVMe over Fabric for connecting to the and I see a lot of questions saying like we cannot hear you. I hope it's not muted now. Right. Apologize for the technical problems that we have been having for the Q&A. Feel free to ask the questions and continue the conversation in the maintainer track Slack channel. Thank you.